Well, students, today we are going to start our final chapter on waves, sound, and music. And today we're going to talk about music, the application of these waves to creating musical sounds and musical instruments. So with that, we'll go ahead and get started. The three main qualities that we are going to talk about are pitch, intensity, or loudness, and something that's not on this slide, which is called tone or timbre. So that is another aspect. So those three things, actually it's listed here as quality here. So pitch, intensity, and quality. We'll talk a little bit about how musical instruments produce those sounds and those waves, and then we'll finish up with a little bit on Fourier analysis. First of all, noise corresponds, as you see here, to an irregular vibration of the eardrum. It does require vibrations, but they are not in any systematic, repetitive wavelength or frequency. Noise tends to be a jumble of all of the different wavelengths and amplitudes. And white noise is a mixture of frequencies that usually span the entire range or sub-range of frequencies. Now, we're going to talk about aspects of sound that are not related to noise, but do have periodic patterns of intensity. And these periodic patterns of intensity are characterized by their frequency. The primary effect of musical sounds is that they have periodic tones, or what we might call periodic intensities, which are composed of multiple frequencies that are present at the same time. But these multiple frequencies have to be brought together in a special way to create the sensation of music as opposed to just a pure sound or noise. So a sound of a siren, for example, may start at low frequency and gradually change to high frequency. We talked a little bit about how this could also be produced with the Doppler effect. If you have a siren that's moving towards you, its pitch is higher than when it's stationary, and when it's moving away from you, its pitches or its frequency is lower. The three characteristics that we're going to talk about are pitch, intensity, and tone. The pitch is determined by the frequency of the sound waves which are received by the human ear. They're determined by fundamental frequency, which means that there is a minimum frequency that is present in the characteristic of music. And then there are multiples of that, but that's according to each instrument. In other words, we have the lowest frequency on the string of one string of a violin, and that's called the fundamental frequency, which is its lowest one. But that may in fact and will in fact be different than the lowest frequency that occurs on an oboe or a cello, for example. We're going to talk a little bit about how the fundamental frequency, which is of a stringed instrument or a wind instrument, is a minimum minimum frequency that the instrument will produce. And every other frequency that it produces will be a multiple of that frequency. And we'll talk a little bit about that a little bit later, too. Intensity is given in terms of, well, I shouldn't say it's given in terms of watts per meter squared, which may not ring a bell for you, but it is the correlation of what we call loudness. When we hear a sound that's quite loud, the physicists would say that it has a higher intensity, which means there is more power in the compressed part of the molecules that are arriving at the ear. There's a higher compression of air molecules within each frequency that gives it a characteristic of loudness. So when we get the maximum compression of air molecules traveling at the speed in air, which is what we'll be dealing with primarily here, 330 meters per second, will yield a maximum pressure on the eardrum. So if that maximum compression is higher, we experience it as a louder sound. We can measure that in terms of the rate at which that compressed air is hitting our eardrum. and that will give you our unit that we'll talk about. Finally, the tone or quality is the aspect of a musical instrument that uses the higher frequencies produced by the string or the wind instrument, but it's produced in a way, those higher frequencies, such that they are multiples of the fundamental frequency. So for example, the key of C on the piano, the middle C, might be 261 hertz, but there will also be multiples of that present, which would be, for example, 560 hertz, for example. So let's see, if I double 260, I will get about 520 hertz. And then there will be another frequency that's 3 times that value, or 3 times 260 hertz. So anyway, the point is that every instrument not only produces what we call the fundamental frequency, which is, or every given string, it produces the fundamental, but it'll produce multiples of that frequency. And the way in which the relative intensities of those multiples add together give us the perception of the tone of the instrument, which allows us to distinguish, for example, the 260 hertz fundamental frequency on a horn or clarinet with that from the piano. So different musical instruments are obtained by changing the frequency of the vibrating sound source. And it's usually done with altering the length, the tightness, or the mass of the vibrating object, the most common one being the string. So if I tighten a string on a piano, on a guitar or a violin, I will get a higher pitch. So important thing to note here is that pitch in a physics sense is really talking about frequency. What is the frequency of the vibration that is reaching your eardrum? So and as with all other, as with transverse waves, we characterize them by their wavelengths, so that every frequency of sound will be associated with a unique wavelength. And the way we know this is that frequency times wavelength is the same for all frequencies. It is, in fact, the speed of sound, which is 330. So if I lower the wavelength, I increase the frequency, and vice versa. So in a stringed instrument, the pitch is the frequency of what we call the first harmonic, which is shown in the top figure. And it is given by oscillations of a standing wave. So we've talked about standing waves before as they exist in a tight rope that's being plucked or a stringed instrument. And when we do that, we pluck it, there are certain wavelengths and frequencies that will be allowed for the fact that the endpoints of the string are fixed. They are not allowed to move. So the only way in which we can obtain a sound from plucking a string is either to generate the first harmonic, which means that the purple magenta line will oscillate up and down, where you see the maximum oscillation at the top, the minimum oscillation at the bottom, and then it goes back to maximum again. So it just, the middle of the wave oscillates with the maximum amplitude, and everything else is less, and the nodes, which are the points of zero movement of the string, occur always at the end. So we call this this first harmonic wave of a string instrument the fundamental frequency. The first harmonic frequency is, as we've said, is also called the fundamental frequency. Most musical sounds are composed of a superposition of many or at least several different frequencies that are multiples of the first harmonic or multiples of the fundamental frequency. So when you pluck a string, and you may pluck it at a point which is not in the center, for example, closer to one side than the other, then you can make these excursions of the string such that at one point in time it follows the upper curve where my arrow is showing and then comes back down and ends up at zero at the fixed point on the end, and then a half a cycle later, or a little bit later time, that it begins to diminish, and on both sides of the center line, and then eventually it goes negative, and the string position is somewhere down, as like I've shown here, and then it goes back to its original position. And the time it takes to go from the original maximum oscillation to the left of center line to back to maximum oscillation again at that same point is given by the period of the oscillation. And as we've talked before, that is equal to the inverse of the frequency. So most musical sounds are composed of superpositions of these different, we call them harmonics. And sometimes they're called partial tones. So we may think now, and we'll talk more later about tone, but tone is the subjective impression that we have when in fact what we're hearing are multiple frequencies that are all multiples of each other. And we'll talk a little bit more about that a little bit later. And finally, the bottom figure, which is the one that's shown with the blue oscillations of the string, is a composition of the first and third harmonic. So not only is the bulk of the string oscillating as like it would in the first harmonic, which would be from this dotted line in the top, dotted line in the bottom, but within each of those there is also oscillation between the nodes that are located at the 1/3 point and the 2/3 point of the length of the total length of the string. So in this case, if I were to see a moving picture of that, I would see the first harmonic oscillation where the bulk of the string is going back and forth and with maximum amplitude in the middle, but we would also get other amplitude oscillations that you see here in time, and there would be therefore a combination of the first and the third harmonic. And this is what gives us the idea or the notion of tone, which is, as we said, subjective. One thing to note is that higher harmonics have shorter wavelengths. And so you can see here that if I go from the first harmonic to the second to the third to the fourth, the wavelength of the oscillations gets shorter and shorter. As a result, and because of the fact that the wave speed, remember these standing waves are produced by waves going from left to right, from the node on the left to the node on the right, back and forth. And these are constantly two waves that are moving past each other that add up to give us this very pretty systematic structure of the motion of the entire string. But because of the fact that we have these different wavelengths, then as a result, each one of these does produce a different frequency. So we mentioned before that wave speed is equal to frequency times the wavelength. So if the wavelength is getting shorter, then the frequency that's produced by the string is getting higher. So the second, third, and fourth harmonics will all be higher pitch or higher frequency than the fundamental. And that's what's shown here. So the second harmonic has half the wavelength and therefore twice the frequency, this one, as the first harmonic. And the third harmonic has 1/3 the wavelength and therefore 3 times the frequency as the first harmonic. And the fourth harmonic will have 1/4 the wavelength of the first harmonic and therefore 4 times the frequency of the first harmonic. So we get these multiple frequencies occurring that reach our ear, and they occur in various intensities. So in other words, we might get a lot of intensity from the first and third, but very little from the second and fourth. So that would give us one sensation of tone, even from an instrument. While another instrument, while having the same first harmonic, might have very high first and second amplitudes. As I say, they contribute a great deal to the total sound, but the third and fourth have very little. So that would give us a different tone. So the weighting, or how much intensity comes from each of these different frequencies, is what we classify as the tone of the instrument. So the subjective qualities of sound is what we call timbre and tone. The objective qualities of sound are the frequencies that are associated with them, and these are the higher harmonics that we've just talked about. How much higher harmonics is present in any given string when we pluck it. But what is clear is that we can certainly always, even though two instruments, the piano and the clarinet, have the same pitch, which is to say the same fundamental frequency, we can very easily tell the difference in their sound because they have different harmonics that are contributing to it. Now, the tone of each instrument has a characteristic sound that differs in the relative intensities of the first, second, third, fourth, fifth, sixth, all the way up harmonics of each note from one instrument to the next. And by each note, I mean in each fundamental frequency. So the timbre or tone describes all the aspects of a musical sound other than pitch, loudness, or how long we leave the note lasting on our instrument. And so those together form the complete set of physical properties that are unique to music as distinguished from our voices or our talking voices or horns or other sirens and other things. And as we've sort of mentioned before, and hopefully we'll repeat again, the partial tones are the ones associated with the harmonics of the fundamental frequencies. So partial tones would be, if I hit the key of C on the piano, that has a fundamental frequency of 260 hertz. So then if I then double that frequency to 520 hertz, that would produce the partial tone of that harmonic. So again, it's just associated the subjective part of how we view music, which is tone, with the actual thing or the physical property, which is called the harmonics. Now their frequencies are always, I should say, whole number multiples of the fundamental, and that's what uniquely characterizes them by their partial tones. So the quality of a tone is determined, as we said, by the presence and relative intensities of the various harmonics, which are called partials. The sound produced by a certain tone from the piano and a clarinet of the same pitch have different qualities that the ear can recognize because they have different combinations of these multiple frequencies or different intensities associated with each of the higher harmonics. A pair of tones of the same pitch but with different qualities have differences in these relative intensities of these higher harmonics. And here you see a picture here of the primary frequency, we would call the fundamental frequency, which if this was a piano C, a middle C, this would be a structure that goes up and down at 260 hertz, or to say your ear would be hearing the air compressions on your ear 260 times per second to give you the sound of the middle C. But within that, there can be higher frequencies present, and 2, 3, 4. For example, you see these peaks in here, which occur more frequently. They're closer together, and they would be at 6 times the fundamental frequency. So it would be 260 times 6, whatever that number would be. That would be the higher harmonic of the C. But in the clarinet, with the clarinet playing the same pitch, we get a different structure of harmonics. There will be a different intensities associated with them, and you can see that the time structure, which is what this is displaying, this is showing the time structure of the intensity or the pressure of the compressions of the air molecules are different in these two cases, even though they have, in fact, the same pitch. So music is organized on many different levels. Most noticeably are musical notes. Each note has its own pitch, so that's what we mean by that is the base of the fundamental frequency, the lowest frequency at which the vibration can occur for that instrument, whether it's a string or a wind instrument, and we describe that pitch by its frequency. And if we have rapid variations of the sound source, then that would be what we call high frequency. And if we have slow variations, where the compressions arrive at the eardrum more slowly than the others, then that would be what we would call low frequency or a low pitch. So the pitch is the lowest frequency that the instrument can produce for a given string, or in the case of a wind instrument for a given length of its extension, or if it's a flute for a given number of holes that are covered in the tube of the flute. Musicians give different pitches, different letter names. So we have the letter names A, B, C, D, E, F, G. You know that some music is, some songs are developed in the key of C, some are developed in the key of D, some in the key of E, etc. So what do these different letter designations tell us? Well, they basically are letters that designate different fundamental frequencies. So in the case of the piano keyboard, we have the C's, the note C that are labeled here. And the characteristic feature of how we define frequencies on a piano is that if you take a given frequency, a given a key on the piano, for example, this would be the middle C right here, that 261 hertz. If we take a given key and we hit it, then the key that has twice that frequency would also be in the key of C, and a key that has double that again would also be in the key of C. So we call each of these groups between key of C's, we call these groups an octave. So an octave is basically a range of frequencies that go from A, B, C, D, E, F, G back to A again. So these repeat, A, B, C, D, E, F, G. Then we go A, B, C, D, E, F, G, A, B, C, D, E, F, G. So there are 1, 2, 3, 4, 5, 6, 7. There are 8 notes or divisions of frequencies in each octave, and we, on a piano keyboard, we cover a little over 7 octaves. So starting at the very bottom of around 37 hertz, which is the lowest frequency, up to the maximum, which is at about 4,186, which is the last key, C key on the piano. And in between that, between C3 and C8, there are 8 primary notes, and between C4 and C5, there are 8 notes. It goes A through 8, goes C through C. So we have D, E, F, G, A, B, and then C again. So this was the way in which we label the frequencies by these letter designations A, B, C, D, E, F, G. And notice that the A, B, C, D, E, F, G does not uniquely give a frequency, because just as with the C's, you can have a very low C at 37 hertz. You can double the 32.7. You can double the frequency to get 65.4, and then you double that and you get 130, and if you double that, you get 261. So at every octave, we double the frequency, and there are 1, 2, 3, 4, 5, 6, 7, 8 C keys on the piano keyboard, with 32.7 hertz being the lowest frequency and 4,186 hertz being the highest. Similarly, for all these others, there will be A, B, C, D, E, F, G, all the way through, that repeat from A to G, and then A to G, and A to G, A to G, A to G, as we go up the piano board with higher frequency notes. So this is basically a way in which we characterize the pitch of each individual string on the piano keyboard. Now, the high-pitched sounds used in music are most often less than 4,000 hertz, but the average human ear can hear sounds up to 18,000 hertz. Some people and some animals can hear tones of higher pitch than this, And one thing worth noting is that as people grow older, and particularly in old age, they all begin to experience hearing loss, and so do dogs and cats and other animals, but they tend to lose their upper limit of hearing before they lose their lower frequency of hearing. So if you're talking to someone hard of hearing, try to use as low voice as possible with as highest intensity as you can. So that's just some things to keep in mind as we go through this.